Welcome back, ladies and gentlemen. Here we are looking at this way of looking at numbers called scientific notation. Sometimes, maybe not so often in this country, but sometimes you might hear this called standard form. So, why is this important? Well, if you're ever going to deal with a very large or very small number, then scientific notation becomes a much easier way to write it, and you'll see that. But on top of that, you're likely to make fewer mistakes when you write these numbers and when you calculate something with these numbers in scientific notation. Fewer mistakes is always nice. Before we get into the form and what they look like and all that, let's look at these things called powers of 10. Any power of 10, when you multiply something times a power of 10, for example, something times 10 to the third power, all that's doing is moving the decimal place or decimal points 3 places. In this case 3 because you have this exponent of 3. This is 10 to the power of 3. So the exponent is positive, so it will move the decimal to the right, and it will move it 3 places. If you are multiplying by 10 to the negative 4 power, that's going to move the decimal 4 places because of the 4, but you're moving it to the left because the exponent is negative. Scientific notation uses powers of 10, and you'll see that. The format of scientific notation, what is it? Well, it never looks like this, but how is this arranged? What's going on when you see scientific notation? Well, there's always going to be one digit to the left of the decimal, in front of the decimal, just one. After the decimal, there might be no digits. There might be 1, there might be 17. After the decimal, you're going to have as many digits as needed for after the decimal for the correct number of significant figures in that number. And so here's where your flexibility comes in. All your sig figs are sort of adjusted or determined after the decimal point. Otherwise, you just have one sig fig in the number here. The power of 10 does not really count for your sig figs. It's not, although it is part of the number, it's just moving the decimal point around. So one more thing about this. What about that power? What about that exponent? The power of 10, and its purpose is that it correctly locates the decimal. You'll see that. So this is the general form. You'll see a number here. You'll see one or more numbers after the decimal here, and you'll see a number here in the exponent. These numbers here in the front could be positive or negative, and the exponent could be positive or negative, as we've seen here. Positive means you move the decimal to the right. Negative means you move the decimal to the left. An example of this, and this is kind of an extreme example. We're looking at the mass of a proton measured in kilograms. And yeah, so how many zeros is that? It would take you a bit of time to count them up. As you're writing a number down like this, you're also likely to make a mistake in writing the wrong number of zeros. Look how many there are, and that means it's so easy to lose track of a few of them or to add an extra one here and there. And so scientific notation is going to help us eliminate those potential problems. We rewrite this. We take the first significant digit, and that's the 1, and then we have 0.67. So we're moving the decimal point. But to make sure that we're talking about the exact same value, we multiply by a power of 10. In this number, from this location, we have to move that decimal point to the left. So we have to have a negative exponent, and we have to move it to the left 27 places. So we have a 27. So negative means to the left, and 27 means 27 places. And you can count them. 1, 2. I'm not going to do the whole thing. You can do that. But that's what's going on with scientific notation. Look how much easier this is to write, how much faster this is. And if you do it this way, well, it's easier to keep track of this. Now, there's one thing about this. There are not 27 zeros between the 1 and the decimal point. That's not what this is telling you. It's telling you that the decimal point has moved from this location, right here, 27 places to the left, to there. And so these two numbers are equivalent. But how much nicer is this one? Yeah, I know. So what about some other examples? You have here in this little table the decimal version of several numbers and the scientific notation version of the same numbers. So the decimal version of number 2 and the scientific notation version 2 times 10 to the 0 power. Oh, that's odd. But that equals 2. Why? 10 to the 0. Anything to the 0 just equals 1. So you have 2 times 1. That's 2. Same thing. The decimal number 300. That would be 3 times 10 to the 2nd power. From the 3, the decimal sort of resides here. I want to move the decimal point 2 places to the right. So, and I get the same number. This one, 4,321.768. Scientific notation. And not such a huge advantage here because we still have to write all this business. But you can see how this is working. We're going to move the decimal 3 places to the right to get it back where it was before. Right? What about negative numbers? Negative 5,300. Well, the negative stays in front here. And scientific notation, negative 5.3 times 10 to the 3rd power. The 3rd power here means we move the decimal point 3 places to the right. So from here we go 1, 2, 3, and there it is, equivalent. 0.20. There's 2 sig figs here. So here's an illustration of why scientific notation can also be useful, because it lets you take care of sig figs very easily. This would be 2.0 times 10 to the negative 1. From here, we move the decimal point 1 place to the left. It'll go right there, just like that. And finally, 0.00082. Well, even with just 4 zeros here, it's kind of easy to lose track of one or to add an extra one accidentally. 8.2 times 10 to the negative 5. So much nicer. You're much less likely to have a mistake. All right. Question for you. Do I actually have the right number of zeros there? Compare to this number and see. Thanks for watching. I'll catch you next time.